Welcome back, everyone. I'm Jordan Giesecke, and this is The Limiting Factor. This is part 8 of the Lithium Mine to Battery Line series to break down and understand what was unveiled at Tesla Battery Day. This video will address 3 persistent myths that I've seen repeated since Battery Day. 2 of these myths relate to Tesla Silicon, and so they're best addressed as part of this Tesla Silicon mini-series. Before we begin, a special thanks to my Patreon supporters and YouTube members. This is the support that gives me the freedom to avoid chasing the algorithm and sponsors, and I hope will eventually allow me to do this full time. The links for support are in the description. Back to myths. Myth 1. Tesla will be jumping directly to 100% silicon anode. Many people assume that Tesla will no longer be using graphite in their batteries and will completely replace graphite with silicon in the near future. This isn't the case. Even before Battery Day, Elon tweeted that silicon graphite anodes make sense, but the salient question is, what ratio of silicon to carbon and what shape? Shape was covered in the last video. That's only a data point of 1, so let's take a look at what was said on Battery Day. Drew said that there is silicon in current batteries, but what Tesla is proposing is a step change in the capability and cost by going to the raw metallurgical silicon. In other words, what Tesla is proposing is simply a change in the type of silicon used, which is currently silicon oxide glass. There was no mention of removing graphite. Elon said that if you can use simple silicon, it's dramatically less than even the silicon that's currently used in the batteries that are made today, and you can use a lot more of it. In other words, metallurgical silicon is cheaper than what's currently used in Tesla batteries, and you can load up the anode with higher ratios of silicon. At no point did Drew or Elon say 100% silicon. They simply said more, which implies an increase in the ratio of silicon to graphite. Why weren't Elon and Drew more clear with their wording? My guess is that it's because they have basic assumptions about what's possible. If your basic assumption is that 100% silicon won't be possible for another 7 years, you wouldn't think to clarify the wording because you have a progression path in mind which involves steady increases. The past 3 videos in this Silicon mini-series covered the science of silicon graphite anodes, which illustrated clear pathways to address the technical challenges of a 20 to 30% silicon loading for mass production. I can't say the same for 100% silicon loading. There may be technical solutions out there to do 100% silicon anodes at a scale and cost comparable to current lithium-ion batteries, but I haven't seen evidence of this yet. I do expect evidence to start emerging in the next couple of years, but there will be a lag between evidence and production of several years. Looking more deeply into the presentation, the right-hand panel on this slide indicated to me that Tesla is still using graphite anode and mixing it with silicon. On the right is what looks like potatoes and rock salt held together with ribbon. The potatoes are graphite, the rock salt is silicon, and the ribbon is binder. We know the rock salt is silicon because in the center panel they describe it as silicon. The potato-shaped particles clearly aren't silicon, and I have yet to hear a suggestion that makes sense other than graphite. From my experience doing 4 months of research into graphite anodes, the potato shape is immediately recognizable as graphite anode. The size of graphite anode particles ranges from 10 to 40 microns in diameter. The ideal size of silicon for a graphite anode would be 1 to 10 microns. In other words, the size and shape differences of the potatoes and rock salt clearly aligns with the size differences we'd expect between graphite anode and silicon. There's further evidence of a 20 to 30% silicon loading with graphite if we look at the cost information provided in Tesla's Battery Day slides. Tesla claimed that Tesla Silicon increases range by 20% and reduces cost by 5%. How can both of these things be true at the same time? It stems from the fact that the anode is 9 to 11% of the battery cost at the cell level, 15 to 20% of the weight, and 50% of the active energy storing material. Balancing all that out isn't really possible with a simple analogy. So I've built this model that compares the cost and energy capacity of Tesla's current silicon oxide battery cells with Tesla silicon cells. I've entered dozens of permutations of numbers into this calculator. What's showing on screen is just the last calculation I made. I've consistently come up with a loading of about 30% silicon to hit the 5% cost target figure. So why do I frequently say a silicon loading of 20 to 30%? It's because in order to hit a range increase of 20%, I found that a minimum silicon loading of 20% is required. I say minimum because this doesn't include the weight of materials like the current collector foils, separators, and electrolyte. I'm working on locating a calculator to nail this number down with more accuracy. But for now, we'll say that 20% silicon is the minimum to hit the range target. That is, at 20% silicon, Tesla hits their range target, and at 30% silicon, they hit their cost target. If I knew Tesla's current pack cost compared to their cell cost, the exact anode cost as a percentage of the cell cost, and the exact energy density of Tesla silicon, I could probably nail this down to within 1% or 2. The key takeaway is that the silicon loading isn't anywhere in the ballpark of 100% silicon. Myth number 2. The graphite anode is now dead. This isn't the case. Graphite in anodes is far from dead and will be around all of this decade and probably the next at massive scale. If Tesla is able to increase the amount of silicon in their batteries to a loading of 20 to 30% in the anode, it means that their consumption of graphite per terawatt hour will reduce by about 50%. However, Tesla also effectively announced that the number of terawatt hours produced in 2030 will be double what we expected thanks to Tesla's efforts alone. In other words, in terms of global demand, we end up right back where we started. 50% less silicon per terawatt hour, but double the amount of terawatt hours produced. Furthermore, most of the factories that are planned around the globe have been planned with graphite in mind, and they won't be making any last-minute changes to their plans. Each of these gigafactories is a hungry animal that needs massive supply lines set up years in advance. As discussed in the last video, the entire battery industry has been expecting the amount of silicon in batteries to increase well before Battery Day. In fact, several companies that produce graphite are actually offering their own composite particles made of graphite and silicon. We may never see 100% silicon anodes because they may always require some sort of elastic network to absorb expansion stresses, but that's a topic for another video. Myth number 3. In the Battery Day presentation, Tesla used range and cost as two of their primary metrics. There are claims that the 54% range increase and 56% cost reduction can be multiplied to provide a cost reduction of something like 70%. My view is that they can't be multiplied. I say my view because this was never actually clarified at Battery Day. The improvements were broken down into range and cost with no qualifying statements. In other words, is this an and situation or an or situation? They did say and, but that doesn't actually help. Both the range and cost figures would be true, whether it's an and or an or situation. I decided to look at this from 3 perspectives. First, range can be simplified to watt-hours per kilogram, and cost is represented by dollars per kilowatt hour. That is, cost over energy and energy over weight. If we attempted to multiply these two, which isn't really possible and we'll discuss in a moment, it results in cost over weight. It doesn't result in a compound reduction in cost, but instead, a different type of metric. The second way of looking at the multiplication problem is to view it from the lens of double counting. For example, both the range increase and dollars per kilowatt hour reduction list cell-to-vehicle integration, cathode material, anode material, and cell design. Cell-to-vehicle integration results in a 14% range increase and 7% cost reduction. This is because it cuts a huge amount of weight. However, the weight that's being removed is steel, which is cheap. The 14% and 7% figures are looking at the same innovation through 2 different lenses. One is cost, one is weight. Multiplying 14% and 7% would be double counting because you'd be counting the same innovation twice. The third way of looking at the multiplication problem is to humor the idea and look at what a 70% cost reduction would mean. If we assume Tesla is currently at $110 per kilowatt hour at the pack level, then multiply by 30%, we arrive at $33 per kilowatt hour at the pack level. This is below the cost of materials needed to make a Tesla 4680 battery cell. For example, the cost of the nickel cathode alone is about $33 per kilowatt hour, and that's before adding the cost of the current collector foils, separators, electrolytes, cell casing, welding, and electronics, not to mention non-material costs such as capital, labor, real estate, consumables, and logistics. So, $33 per kilowatt hour just isn't on the cards for now. To summarize, Tesla already gave us the cost reduction in terms of dollars per kilowatt hour. Multiplying range and cost isn't arithmetically possible, it's double counting, and it would reduce the cost of the battery pack to below the materials cost. Myth number 4 isn't so much a myth as a clarification of this animation. The animation of lithium ions entering a silicon particle contained some artistic license. The lithium ions would actually alloy from the surface of the silicon particle inwards, rather than appearing to inflate from the inside out. A proper animation of anything that's photorealistic takes quite a bit of time. Making it technically accurate rather than just making it look cool adds an order of magnitude more difficulty. Even with an excellent, time-efficient animator, I can spend hours communicating with the animator for something that's 20 seconds long. The pace that I'm putting out these videos forces me to limit the time that I have for animations, and in this case it resulted in a shortcut. On that note, the animations can also easily cost hundreds of dollars for a 20-second clip, and I want to say a special thanks to my Patreon supporters who made those possible. For the video on Tesla charge rates, for example, the cost of the animations exceeded the YouTube ad revenue by about 50%. Back to the main point. One thing that was accurate about this clip is the fact that the diameter expands by 50%. This might be a head scratcher because I've said so many times that silicon expands by 300% as it charges. The trick here is that a 300% volume expansion only results in a 50% increase in diameter. There were requests for me to cover off 2 more myths, but these quote-unquote myths will be covered off later in this Lithium Mine to Battery Line series. First, I was asked to make it clear that a million-mile battery was unveiled at Battery Day. This is true to a certain extent. However, the reality is more complex, more interesting, and opens more doors than you might expect. I was also asked to bust the myth that Tesla said they will not offer vehicle-to-grid in the future. This will be covered at the same time that I cover off my thoughts on a million-mile battery, because the two innovations are inextricably linked. I'd love to do more videos on silicon. The more I learn about it, the more interesting it becomes. As Drew said at Battery Day, difficult problems are fun. Silicon anodes are one of the most difficult problems there is. We can expect to see many more developments in silicon, and rest assured that I'll keep you informed. My view is that for now, Tesla Silicon appears to be the best all-around approach to silicon anodes. Other manufacturers will need high-loaded silicon anode solutions of their own, and something competitive may yet crop up. There are companies like 1D Materials that have promising approaches to tackling a high-loaded silicon anode that weren't covered in this series. We also didn't cover the potential binder and electrolyte alternatives. We focused mainly on active materials in this series like Tesla Silicon, composites, and silicon metal alloys. In the Cracking the Silicon Code video, all I really gave was a tease for binders and electrolytes. Binders and electrolyte solutions are each entire areas of study equally as daunting as the active materials themselves. However, I'm sure many of you are itching to hear more about the rest of what was unveiled at Battery Day. In the next video, we'll dig into Tesla's cathode, which was one of the biggest surprises of Battery Day for me and revealed a lot about Tesla's strategy, both in terms of engineering and product impact. If you enjoyed this video, please consider supporting me on Patreon with the link at the end of the video, or snag something off the merch shelf below. I'm also active on Twitter and Reddit. You can find the details of those in the description, and I look forward to hearing from you. A special thanks to Joel Sapp, Alex Villanueva, and Andy House for your generous support of the channel, all the other patrons listed in the credits, and my YouTube members. I appreciate all of your support, and thanks for tuning in.